So S is, in what direction is the energy? In what direction is the energy?
I have.
I have, yeah. And the direction of the wave propagation, it's in the same direction as E cross B, right? So this S, the energy, is directed in the X direction, in this case, which is the same direction as E cross B. So if I want to write this as a vector, S, it's 1 over mu naught, right? 1 over mu naught, and then it's E naught, B naught, sine squared kx minus omega t, and then it's in the I hat direction, right? It's in the I hat direction. Now what is E naught times B naught sine squared? That's E naught sine, and then times B naught sine. And so S is in fact can be written as 1 over mu naught E cross B. Okay? Yes? Because E cross B gives you the I hat. And then the rest is just E naught B naught sine squared. And then what's in front is the mu naught. In fact, I have a problem that I'm going to do soon, where we find S. Now this S has a special name. First of all, what does it mean? It's the energy per unit of time, per unit of area, and it gives you also the direction where the energy is heading. And the name of it is the pointing vector. Not pointing like a point, but with a Y. It's somebody's name. It's the pointing vector. Okay. So this is the pointing vector. Okay. The intensity is the time average of the pointing vector. Intensity which is the energy per unit of time per unit of area. The average energy per unit of time per unit of area. Intensity I is equal to the average of S, the average of the magnitude of the pointing vector. Now, the average here, I mean the time average, right? How much it is on average over time, not the instantaneous. This one gives you the instantaneous. So mu naught is a fixed number, the amplitudes are fixed, E naught and B naught. So what's the average of sine squared? What's the average of sine squared?
0.
The average of sine would be 0 because it's sometimes negative, sometimes positive. But sine squared is never negative, so it can't be 0. Yeah. So let me ask you, would the average of sine squared be more, less, or equal to the average of cosine squared? Equal. Good. What is sine squared plus cosine squared? 1. Well, each of them would be a half of that. So the average of sine squared is a half. Yeah. And you can prove it by doing the average of a function is you will over a period would be 1 over 2 pi, the integral from 0 to 2 pi sine squared dt. You will get a half. But the quick way is it is a half. So in fact, the average of the average of sine is a half, the rest is a constant, so it will just be this. 1 over 2 mu naught E naught B naught. That's the intensity. Okay, after all this work, we got the intensity now. Let's see, I think I have a couple of problems. The only downside of having to write on the board is I have to write the problem. But that's okay. by the way, this, if you want to eliminate B naught and write it in terms of E, it's equal to, yeah, that's okay, we'll leave it as this. So, yeah.
What's the S, what's that?
The brackets here?
Yeah.
Average. Yeah, it means the average. Okay, let's do an example. The first example I'm going to do, let me first make sure I have some markers. No, we don't.
You can steal from my phone.
We could, unless there is a class in that room. Well, let's do this. Let's just write the problem here on this board, and then if needed, I will erase the other board. So here's the example. Suppose, so this is an example. You're given this, E is equal to minus E naught sine of ky plus omega t times I hat, and then B equals to minus B naught sine of ky plus omega t j hat? No, k hat. So for a change, in what direction is this wave moving or propagating? Huh? The y-axis? Negative, right? Because it's plus. So it's propagating in the negative y direction. And we get it a different way. Okay, we get it a different way. So the direction would be in the negative y direction. So let's find the Poynting vector. Find S. Just find S. How would you find S? You would do E cross B times 1 over mu naught, right in front? Yeah, please do that. You have 3 or 4 minutes to do it. I will let you do that. Let me pause this so it doesn't sit idle. So let's do this one. So the Poynting vector S is equal 1 over mu naught E cross B. So I get 1 over mu naught minus E naught sine of ky plus omega t I hat cross product with minus B naught sine ky plus omega t k hat direction. Okay. Minus E naught times minus B naught, just E naught B naught, right? So we get 1 over mu naught E naught B naught, and then sine times sine is sine squared. And now the cross product. I hat cross k hat is j hat or negative j hat? Negative j hat, yeah. The I hat is in this direction, k hat is in this direction. So if you do I hat cross k hat, it will be down.
Right hand.
Right hand, yeah.
Oh.
Yeah, so it will be in the j hat direction, but negative. So the Poynting vector, remember, is in the same direction as the wave traveling, right? So it's minus j hat. Yeah, so the direction of motion, this confirms that it's in the minus j hat direction. Okay. Direction of propagation is minus j hat direction. Okay. Yeah. The next product that I want to show or want to do, let me write it down. I don't want to So let me pause this and then write it down. So let me read the problem again. So example 2, it says at the upper surface of Earth's atmosphere, the time averaged magnitude of the Poynting vector is 1,350 watts per square meter. What is the time averaged Poynting vector? What is that trying to say?
Average of us?
What's the average of S called? Intensity. Yeah, so that's just the intensity. So they're just saying the intensity is this, okay? Yeah. Assuming the sun's radiation is sinusoidal, meaning it's just like one of those, a sine function. Find E naught and B naught, and then it says here, what is the time averaged power? What is the average of the power radiated by the sun? And I need to give you actually the distance from the Earth to the sun. So the distance from Earth to the sun is R equals to a large number. 1.5 times 10 to the 11 meters. Okay. Let's please take a few moments to think about this and then do it, and then we will go over. Okay. So I'll give you 2 or 3 minutes. Let's just focus on part A for now, okay? We'll worry about B. So let's continue it. Yeah, good. Yeah, the electric field is about 1,000. So a good starting point would be here, right? That's a good starting point. So we know for part A, the intensity is E naught B naught over 2 mu naught, which is E naught. B naught is E naught over C, right? So it would be E naught squared over C, 2 mu naught C, like this. And so E naught would be 2 mu naught C times I over the square root. Okay. So hopefully this works out to be about 1,000. Units of electric field? Newtons per coulomb, right? Or a volt per meter? It's a volt per meter or Newton per coulomb. Okay, so please double check my work. I think I got it, but it should be 1,000 or 1,001, something, or 1,010, somewhere around along those lines. And then B naught is B naught divided by C. You see why it would be small, because you're dividing by the speed of light. So that over C is approximately 3.4 times 10 to the minus 6 Tesla, right, for the magnetic field. So that's the magnetic field part, right? Now, what is the average power delivered by the sun, given that this is the intensity at the Earth? Remember, intensity is power over area, right? Power over area. So here's the sun, let's say. And Earth, let's make the sun a little bigger. And Earth is somewhere here. It's not to scale, obviously. And the sun is giving off radiation in all directions. This direction, this direction, this direction, this direction. So the Earth would receive just a tiny bit, right? A tiny bit, just this much. That's the amount it receives. So the sun is radiating in all directions. So when you look at the Earth, so think of that power is divided over a very large sphere, and the Earth gets a tiny slice of that sphere. So the power, the intensity, would be the average power over the area, right? Over the area, power over area. This power here is average power. So what's the area of, like, if you have a large sphere, a sphere of radius r? Pi r squared, or 4 pi r squared. That's the surface area, right? Yeah, for a sphere. It's 4 pi times r squared. And so the power would be the product of these. So power would be 4 pi r squared times I, or I should say the average power. Is this. So look, you will do 4 pi times this number squared times the intensity. So that's going to be a very large number, right? It's going to be a very large number. And that number is, I will just write it down, it's 3.8 times 10 to the 26. Plus 3.8 times 10 to the 26. Now, this is a very, very large number, right? Isn't it? It's saying the sun is giving off 3.8 times 10 to the 26 joules every second. Okay? You can look it up. How much energy is consumed on Earth per year? So all the cars, all the heating, all the air conditioning, all the factories, everything. You know how many joules per year? 10 to the 20. 10 to the 20 per year. So the sun emits enough energy to power Earth. In 1 second, the energy emitted by the sun is enough to power Earth for 1 million years. In 1 second. Yeah. So
Earth right now.
yeah, at least, but we get that much. Because we're far. Okay. There is only one little topic left, and I'm going to discuss that, and it's the pressure, radiation pressure. Radiation pressure. We will state without proving that the energy carried by electromagnetic wave is related to the momentum. And the momentum, P, this is momentum. So here's the problem with this topic. We're going to talk about power and pressure and momentum, and they all have P. They all have the symbol P, unfortunately. So the P here is referring to momentum. And momentum is the energy carried by the light over C. And let me write it as U over C.
Is it like P and then subscript M? For momentum?
We could, but then for mass, I don't know, it might get confusing. I'll write it P. Here it's just momentum, right? So this is momentum. And so delta P, the change in momentum will be 1 over C times delta U. Okay. How is force related to the change in momentum? How is force related to momentum? It's momentum over time. Change in momentum over change in time. It's dp dt, rate of change of momentum. So let's say you have radiation falling on a surface, and we want to know the pressure. We're going to assume first the radiation is going to be absorbed by the surface, meaning it's like a piece of clay. If you take clay and you hit the board, it just sticks to it, right? Momentum goes from something to 0. If it bounces off, it's twice the change in momentum, right? When it bounces off. So we're just going to assume it's going to be completely absorbed, not going to bounce back. So that's the change in momentum. So the force, F for force, is the change in momentum over time. And that's equal to 1 over C times delta U over delta T. And so that is the power, isn't it? Delta U over T is the power. So the pressure is force over area, right? The pressure is force over area. So it will be this. 1 over C times delta U over delta T times 1 over area. And we're going to just average all this. I'm talking about the average here. So what is the average energy per unit of time per unit of area. What is that? Huh? Energy per unit of time per unit of area. Energy per unit of time is what? Power. And then power over area is
Intensity.
intensity. Yeah, so it's the intensity. So it's going to just be, so this is just the intensity. So it's going to be 1 over, it's going to be the intensity over C, over the speed of light. That's the pressure. So, but this assumes assuming all absorbed. How did I? Complete absorption. Yeah, let's write it here. Complete absorption. What if it reflects? What's the change in momentum? It would be twice as much, right? Because the momentum is, let's say, this much, and then it bounces, it's in the other direction, the negative, it would be twice as much. So if it's, if it is complete reflection, it will be twice as much. Okay, it will be twice as much. I think I've covered everything I need to cover in this chapter. There are standing electromagnetic waves. I'm going to, we don't need them, so I'm not going to cover those. But it's a small section. It's just some addition of sines and cosines and trig identities. So I think you have everything. You have everything you need to know, or you know everything you need to know to do the homework, which is due at some point. I forget what point. So I have about 10 minutes. Let me pause this.